Sorry guys, my iPad cut off. So a photon is just a particle that has no mass and it's just completely energy. It's all energy. So a photon is massless and has all energy. It's just pure energy. And he says that photons are going to act more like particles. And he says that under the right conditions, photons striking a metal surface can transfer their energy to the electrons in this metal. So they can excite these electrons. If they're exciting these electrons, then we can get electrons being emitted from that metal surface. Now, the intensity of the light in terms of what's happening in the photoelectric effect. The intensity of the light is related to the number of photons striking the surface in a certain amount of time, not necessarily the energy of each photon. So if I have a lot of light, a lot of photons coming in here and striking a metal surface, and then emitting all of these electrons, I can get it's not necessarily the energy that I'm going to get more photons. It's going to be my intensity. How much or how many photons do I have striking that metal surface? Not necessarily how much energy does each photon have. So the more photons I have striking that metal surface, the more electrons that I can have that can be emitted from that metal surface. Not necessarily if I have two photons that have a higher energy, they hit the metal surface and I'll get more. It's if I have a lot of photons coming in here, the intensity. So how many photons I have coming in, if I have a lot of them, they could emit a lot of electrons from that metal surface. So photoelectric effect, like we said, was Einstein. And he also concluded that energy must be proportional then to frequency. So he also says E equals h times v. He agrees with Max Planck that E equals h times v. And we know, again, h would be Planck's constant. And we can also do this experiment to show the photoelectric effect in a lab setting. So I can have an evacuated tube or an evacuated chamber here. We have a clean metal surface, and if we have some type of radiant energy that we can strike that metal surface with, and we have some positive terminal here that's also in this evacuated chamber, if electrons actually were emitted, if electrons are emitted from this metal surface, then those electrons will be attracted to that positive terminal. And if they're attracted to the positive terminal, then that current can flow through the wire into this battery, and then I can see if I would have a current or not on this current indicator. It should make, I should have a flow of current then. So it would go through that battery, and then I could see that on my current indicator there. And we see that that happens. We see that if we have some type of energy here, photons, striking a metal surface, we do have electrons that will go through or be attracted to that positive terminal, and then it's going to show on that current indicator there. So we have actual physical evidence that says photoelectric effect is actually happening. Okay. So if one knows the wavelength of light, one can calculate the energy in one photon or packet of that light. So we know from so far with our light formulas, we have C equals lambda times V. So I have speed of light equals wavelength times frequency. And I also know that the amount of energy in a quantum is h times V, Planck's constant times frequency. But let's say that I just give you the wavelength. Let's say I just give you the wavelength. So for example, we have, we want to know the energy of one photon of yellow light if it has a wavelength of 589 nanometers. So if it has a wavelength of 589 nanometers. So I know lambda equals 589, well, let's just go ahead and say times 10 to the negative 9th meters, because we know we're going to want it in meters anyway. And my goal is to find E. Well, I know that E equals h times V. There's no lambda in there, So crap, what do? Well, I know that lambda is related to v, wavelength and frequency, by another formula, c equals lambda times v. And I know wavelength is 589 times 10 to the negative 9th meters. I know c is speed of light, so 3 times 10 to the 8th. So I could find v to plug v in because I know h is just a constant, so then I could find energy. So let's do that. So I would have 3 times 10 to the 8th meters per second equals 589 times 10 to the negative 9th meters times v. If I get v by itself, I would take 3 times 10 to the 8th and divide it by 589 times 10 to the negative 9th. If we do that, we should get 5.09 times 10 to the 14th per seconds. So now I know v, and I already know h, because that's Planck's constant, and they're asking me to solve for energy, so I could find energy now. So I'm going to take 6.626 times 10 to the negative 34th joule seconds. There's Planck's constant. We're going to multiply that by my frequency that we just found. 509 times 10 to the, or 5.09 times 10 to the 14th per seconds. So if I see here, my seconds are going to cancel out. Energy we know is in joules, so that makes me happy because then that dimensional analysis stuff worked out well. So that would give me 3.37 times 10 to the negative 19th. And that would be joules. Okay. Okay, let's get to our third phenomena. Okay, on our third phenomenon, we have our last mystery in the early 20th century involved the emission spectra observed from energy emitted by atoms and molecules. So in this case, we found that different gases will emit different colors of light when they're excited. So different gases emit light of different characteristic colors when a current is passed through them. On Monday I'll show you, I have an iPad app that's pretty cool that can show like different emission spectrums of different gases or different elements. So we'll look at that on Monday. But this was a big mystery because we were trying to think about how electrons are arranged in atoms at this time, and Einstein really started us off with that, thinking about the photoelectric effect, where I have these electrons that can be emitted from a metal surface because we can excite them, and then they can be emitted. So scientists were starting to think then, the reason that different gases emit light in different colors is because we're exciting their electrons in a different way. And if we're exciting their electrons in a different way to get different colors, it means that they're absorbing or emitting a certain amount of energy. So for atoms and molecules, one does not observe a continuous spectrum. So like if we have a flashlight, if we have white light, and we shine that through a prism, then we're going to see an entire continuous spectrum. I see Roy G. Biv. And I can have, we could also see something with monochromatic light, polychromatic light. Monochromatic light just means that we have one particular wavelength. So we'll see one particular color. Polychromatic light, so poly meaning many, would mean that I could have different wavelengths. The light could contain more than two or more different wavelengths or different colors. So a line spectrum is something that we have seen that can show discrete wavelengths of particular elements. A spectrum, where it says, what is a spectrum? A spectrum is something that is produced when radiation from a light source is separated into component wavelengths. So it's particularly finding at what wavelength do I see a specific color. And the resulting spectrum is going to consist of a continuous range of colors. So if we think about Roy G. Biv, I think about a continuous spectrum. This would be an example of a continuous spectrum. I see all of the colors, all of the wavelengths for that visible light region, because that's what we can see. So that would be continuous spectrum. A spectrum may not be continuous though. We may have something called a line spectrum. And a line spectrum is where we have only radiation at specific wavelengths. So example for hydrogen, I have 4 wavelengths here of light that's represented on this spectrum. Everything else, those black big spaces then, are representing then that absence of color there. So neon, if I compare hydrogen to neon here, I see that neon is showing a lot more wavelengths of color than hydrogen is. And we're going to look at some more of these line spectrums on Monday. But what we're seeing here is that we're only getting a discrete, a very specific amount or a very specific wavelength for color on elements. And each line spectrum, a line spectrum is like a fingerprint for an element or for an atom. And hydrogen, we're always going to see that hydrogen is going to have that line spectrum. We're always going to see that neon is going to have that line spectrum. So because we see that, we have an indication that these atoms can only, or their electrons can only emit or be emitted or absorb a certain amount of energy. Bohr and Balmer were 2 people that really focused on this. In 1885, Balmer showed the 4 lines of the hydrogen spectrum. So he worked on this spectrum here. He tried to find a calculation, a formula that could tell us where the wavelengths would be for each element. We call this today the Rydberg equation. And that Rydberg equation is 1 over, that's my upside down y, so there's lambda, 1 over lambda equals, 1 over lambda equals RH, which is the Rydberg constant. So RH is just my Rydberg constant. And then that's going to be multiplied by 1 over N. N represents energy level. N represents energy level. So NF, meaning the final energy level, minus Ni, which is the initial energy level. So let's go back and... Okay, so my Rydberg equation. 1 over wavelength equals RH, which is the Rydberg constant, times 1 over the final energy level squared minus 1 over the initial energy level squared. Now, N, we said, was energy level. NF specifically would be final energy level. Ni would be initial energy level. RH is called the Rydberg constant, and that is, I don't want to spell this wrong. Rydberg constant. That constant has a specific value, and I'm going to need you to write that value down for me. It is 1.096776 times 10 to the 7th per meter. So Rydberg constant, RH, is 1.096776 times 10 to the 7th per meters. This constant will be given to you. Where can you find it at? On your AP constant sheet, silly children. Okay, are values of N. What do I mean by like energy level? What does it mean by final energy level? What does it mean by initial energy level? Well, let's take a look at that. So let's say, for example, I'm thinking about Bohr's model for an atom, because in a minute we are going to think about Bohr's model of an atom. If I want to do, well actually let's just do it very generically. Okay, so Bohr's model, he was saying that electrons are orbiting around that nucleus in these particular orbits. Let's say that I have an electron, let's do a different color here. Let's say I have an electron that's right here on the first energy level. First energy level is also called ground state. So first energy level, it's going to absorb a discrete amount of energy. It's going to absorb enough energy that it could move from this first energy level, which I would say n equals 1, to n equals 3. It's going to move 2 energy levels. So it can absorb a bunch of energy, and now it's going to move here. So its initial position was n equals 1, and it absorbed energy to move to its final energy level here, n equals 3. When we absorb energy, we move or electrons move farther away from the nucleus. Why? Because the electron wants to be around that nucleus because of Coulombic attraction, right? I have the protons, the nucleus that's positively charged, and I have electrons that are negatively charged, so they want to be in close contact. If they're not close, then it's going to have to absorb a certain amount of energy to be farther away from what it wants to be next to. So we're absorbing energy as we move farther away from the nucleus. And if I wanted to get rid of this energy to go back to the nucleus, then it would emit that energy. So it would release that certain amount of energy. Okay. Which actually, that may be, for right now, I just want us to know our Rydberg equation. We're going to do some problems on Monday where we will use some calculations with that. So that way we can see exactly what I mean. So Bohr's model we have here. Bohr's model, we have orbits are quantized, meaning that an electron can only move from here to here if it absorbs a specific amount of energy. And it can only move from here to here if it releases a specific amount of energy. And again, Bohr says that electrons cannot exist between the orbits. So they have to exist somewhere on that designated path. Or they have to exist here on this designated energy level, or this designated energy level. I'm never going to find one like boom, right there somewhere in the middle. So kind of like our ladder analogy last year for Bohr's model, where I can only gain a certain amount of energy to move up a step, or only release a certain amount of energy, or only use a certain amount of energy to move down a step. I can never just place my foot in midair and then hope that I'll make the step, or just walk up the next step on air. So important vocab here: emission, absorption, ground state, excited state. Emission, we know that emission just means energy of an atom is decreasing, so we're releasing energy here. And in emission, we have an electron moving from a higher energy level to a lower energy level. For absorption, the energy of the atom will increase. So I'm having an atom then move somewhere that's close. It's moving from somewhere that's close to the nucleus to somewhere that's farther away from the nucleus. So in emission, we're releasing energy. Absorption, we're absorbing energy or gaining energy. Ground state. Ground state would be that first energy level, because that would be where the atom or that electron would be most stable around the nucleus. Excited state would be where I could show after that electron absorbs a certain amount of energy, wherever it goes in its final state, it would be considered in an excited state. And that's because it absorbed a certain amount of energy, which kind of makes it a little unstable, a little wishy-washy. Okay, guys, I'm going to end here. So we're going to start on slide 21 on Monday. If you guys have any questions, email me, post on the blog, let me know, and I will see you guys on Monday. Have a great weekend. Bye.